today we are, first of all, we're actually getting this away from my keyboard because it'll kill it. We are erasing a picture of a peacock and a mallard. Goodbye. But that's okay. They're forever recorded in posterity. And today we are also talking about electricity and magnets. And I have combined that. This is not, I didn't make this word up, but I have chosen to combine that on the whiteboard as electromagnetism. That's the title of today's lesson, electromagnetism. Electromagnetism. Now I've got two questions for you. I've actually got three questions for you. The first one is, what do you think the other two questions are going to be?
What is electro?
Mm-hmm.
What is magnet?
There you go. Let's start out with, because I wouldn't say I have a low opinion of your contributions to discussion, but I want to make it as easy for you as I can. Let's start out with some examples. Give me an example of something with electro or electricity or that you've heard of in your life. What's
Tesla.
All right, Tesla, phone, flashlight. I'm going to put flashlight with the PH too.
Tesla coil.
Tesla coil. That one's actually, we're gonna hopefully circle back to that. What about magnetism? Where have you encountered magnets in your life? Or magnetism? Oh, a magnet. Yeah, I'm going to put that one. A magnet. Computer. CT scanner. Some people are coming up with really good ones, actually. And that some people's name is Gavin. What? Oh, yeah, poles. Yeah, I think that's really good. That's really good. And can you tell from the name, this is a yes or no question, can you tell from the name of the discussion that there might be a relationship between these? And what might that relationship be? Well, actually, conveniently, because we've talked about waves already, you should know already what that relationship is. That when we examine the transverse wave of electromagnetic waves, remember this, which direction, since this is a transverse wave, and we can see that the electrical field is oscillating in this case on the whiteboard, it's the up-down axis. Which way must the energy be moving? Nope. In a transverse wave, the motion of the energy is perpendicular to the motion of the waveform. Well, yeah, either left or right on this board, the way we've chosen, or I have chosen to represent it. So if the energy is flowing this way, the electric field is excited in the up-down axis. And the magnetic field, I'm trying to draw this, I'm going to draw it like this. What I've tried to express here, although probably not very well, and because it would be not an impossibility, but these shaded ones should be going out of the board and then into the board, because that's the third dimension. The whiteboard, by its very nature, is two-dimensional, or I mean that's not technically true, but it's a representation of two-dimensional concepts, and it is very difficult for me to draw a third dimension here. But this third dimension is magnetism. So the magnetic field is oscillating in the in and out axis. Do you know what I mean by in and out? Like I can't get my hand into the board. I guess my fingers would probably break before I actually broke through the board. But in and out, right? Does that make sense? Because there are three dimensions. And so if the energy is moving right, one way it can be perpendicular is up and down. And that's what we've indicated with, I should have done this in a different color, would have actually probably been a lot smarter. Red, we'll say red here, is the electricity or electric field, the universal electric field. And black is the magnetic field, and that one's the one that should be going in and out. Does that kind of make sense? Thank you. I'm glad to hear that. They're one waveform, though. Like, this is all one unified object, and we call this an electromagnetic wave. Now, I have a couple things I want to show you. One is this, yeah, we got some, what does this look like on there? Is it, like, if I put this here, is this visible-ish? Yeah, I'm going to try to do it in a way that they're kind of all scattered about. And then I'm going to bring my fairly strong magnet. So we're doing magnet first. Really quite strong magnet. going to bring it over here, and you can see that the magnet is attracting. Can you see? I mean, up. I hope that you can see the magnet. I'm going to pass this around too, by the way. And there's a specific pattern that we're trying to look at, and it's a three-dimensional pattern. So if I put it on there, you can see easily, even in real life, you guys can see easily this two-dimensional pattern. It's kind of like ray-like pattern of the magnetic field coming out. But there's also, if you look, it's hard because this thing is old, but if you can kind of look through the side, you'll see that it has a three-dimensionality to it, that it has there's a depth, that they also have a ray-like pattern going up. So the rays go up and out. Because, I'm going to pass this around, but I want it back. And you shouldn't have your Chromebooks or your phones because of the class rules, but do not let this get near any electronic device. It'll destroy it. Just done. So I really wish it wasn't as near my keyboard as I was earlier. So electricity and magnetism are one phenomenon, electromagnetism, and it's what's called a field force. The forces that both electricity and magnetism, electromagnetism exists, have a great weekend, are field forces, which means that they are non-contact. Do you remember this from, it would have been the second, maybe the third lesson that we did of the year. We talked about contact and non-contact forces. Do you remember that? Yeah. What was another example of a non-contact force? A different example of a non-contact force. That acted on objects even though they weren't touching. No, because wind is actually made of matter, and so the wind is actually physically touching it. Just because you can't see it doesn't mean it's not touching you. Gravity. The marker doesn't have to be touching planet Earth for planet Earth to attract it. So a non-contact force, the other field force that we commonly talk about is gravity. And I want to show you that the equations for these, I really wish I left myself more room over here, but the equations for these, the force of gravity is the universal, you do not have to have these memorized. I just want to show you that they are similar. The universal gravitational constant times the product of the two masses divided by the distance between them squared. The force of electromagnetism is the universal electromagnetism constant times the charges of the two objects divided by the distance between them squared. Again, you do not have to have these memorized, but do you see the similarity? Do you see how these equations look similar? Yeah. That they're both a constant multiplied by the product of the same quantity in two different objects divided by the distance between them squared. So in both of these cases, the field forces, the further away from the source of that force we get, the less attractive it is. Which is why I said do not let this magnet get near your computer, right? Just this existing is not going to fry all the electronics in the room because they're too far away. But if I were to put this, I won't, even though I'm very tempted because I'm just fed up with technology. But I'm not going to put this near the Promethean board, but it would delete it. I mean, it would be a bad situation. It would ruin the screen, certainly. Yeah, I could say that's what my entire life actually for the last month is just looking at a computer and saying that it stopped working. But the closer the objects get to these field force generators, in the case of gravity, massive objects, and in the case of magnetism, charged objects, the closer the objects get, the stronger the forces attract or repel in the case of magnetism. And the stronger the charges are, or the stronger the masses are, or the heavier the masses are in gravity, the bigger the force. So the force gets bigger. Let's put this in very simple terms. Force, bigger. When distance, closer. And in the case of electromagnetism, unlike gravity, which is always attractive, you remember that the law of universal gravitation was that all objects are attracted to all other objects in the universe. Attractive. It's always attractive. Unlike gravity, which is always attractive, electromagnetism can also be repulsive. If we have two positive charges, what will they do when they come near to each other? Repel. If we have a positive charge and a negative charge, what will they do? Attract. Opposites, we often say, attract. And what if we have two negative charges? What will they do? Repel. And this happens with magnets, and it also happens with electricity. The charged particles of an atom, protons and electrons, when electrons are near each other, they repel. When protons are near each other, they repel. But protons and electrons attract each other. And it happens with magnets too. The north pole of a magnet attracts the north pole of another magnet. Speaking of north and south poles of magnets, like we had this example of poles here, if we had a bar magnet that was labeled north and south, as we zoomed in on the atoms of this magnet, what would we find? You should remember this from your study guide. It's as if this magnet was made up. I'm going to erase the signs here. It's as if this magnet was made up of these different areas. What do we call the different areas of a magnet? No, it was a vocab word. Magnetic domains. Magnetic domains. What would we see about these magnetic domains if we looked inside of that magnet? We can't actually visibly see this, but first of all, what would the evidence be that this does exist? Yeah, well, it has poles, and those poles supply a force to other objects. But if we could see them, and if we could look close enough, what would we see about these magnetic domains in a magnet, in what we call a permanent magnet? No, not every which direction, not in a permanent magnet. No. Well, maybe not perfectly, but aligned is what I'm looking for. We would see that they're all more or less. There might be some that are slightly less, but they're all more or less aligned. In fact, the strength of a magnet depends on how well aligned the magnetic poles are. We'll say this arrow is the arrow is facing towards the north. So in a permanent magnet, they're aligned. Poles of magnetic domains, I'll just abbreviate MD, aligned. So in this, it's not called a permanent magnet because it'll be a magnet forever. Due to friction, magnets do lose their magnetism, and there's other ways that they could lose it too. But it's called a permanent magnet because even when it's not in a magnetic field, it still exerts a magnetic field. Now, there are some other objects. What happened?
It didn't break.
It's stuck. Why? Because magnets always stick to everything. This is made out of atoms, protons and neutrons and electrons too. Oh. Well, so how come?
And that's metal, and it attracts.
Okay, there's metal in there, but this, check it out. This you say is metal. So anytime I bring a metal object like this pin towards it, it should attract. Right? The pin, something in this pin does attract magnets, but how come these don't attract them?
Because they're the same.
Nope, they don't push away from each other either. We found out they both do have iron in them. So how come these two don't attract?
Because they don't have aligned.
That's it. You got it. Lizzie said it. They don't have. So they do have magnetic domains. But if we draw, this is going to be the whiteboard. It has the magnetic domains, but they're just not aligned at all. They're all out of alignment. And so why does it have magnetic domains at all? Like if we drew the wall, why doesn't it have magnetic domains? Yeah, and it's not just iron. We'll put no iron, but some elements on the periodic table, and there are other things too, but some iron, nickel, cobalt, some of the rare earth metals, neodymium, praseodymium, I think it's PS, no, it's PR, sorry. Some, due to the arrangement of the electrons, specifically due to the electrons being unpaired, all the single ladies, unpaired electrons, all the single ladies. You know that song?
Yeah.
There, okay, finally. If you could have given me some recognition. All the single ladies, which are the unpaired electrons, are drawn in a particular direction, and that's what makes it have magnetic domains. But in the way that things normally are, those magnetic domains are arranged randomly, and so they don't exert their own magnetic field. But when they come into a magnetic field that is exerted by something else, like, where did my magnet go? When they come into the magnetic field of something else, then they align. So in just this part of the board, although maybe probably not strong enough, I'm trying to show you that the board itself is now magnetized, right? I mean, it's kind of hard to do with the board, but if I had it, yeah, there we go. You can see it there. So the pin is aligned now. Do you see the pin pulling towards the whiteboard? Because the pin has become aligned. the magnet has aligned the magnetic domains in the pin, and then when it's removed, they just go back to normal. Although if I really rub this, I can make it so this becomes something like a minor permanent magnet. But that's what causes the effect of what we see as macro scale magnetism, is when these elements are aligned in these domains. And what's another way to make a magnet? Well, another way is an electromagnet, and that's where we get into electricity. So there are really two kinds of electricity. There are static and current electricity. Static electricity has to do with the accumulation of charges on the surface of an object. Static, what's the word static mean? I mean, you've heard the word static before, like on a radio or something, but that's really referring to static electricity. But can you tell me what the root word of static might be? I kind of be surprised if you got it, but this has to do with, it's the same root as the word stay. So it's it's electrical charges that stay on the surface. And how can you generate static electricity? Give me an example. I'm not looking for like the method. I mean, I am looking for an example of the concept behind it. How could you generate static electricity? Give me an example.
Rubbing your feet on the carpet.
Yeah, if you shuffle your little socky feet across the carpet, which I have both shoes on and I'm not on carpet, but I'm just, you know what shuffling looks like. I guess I don't have to demonstrate that. But if you shuffle your way across the carpet and touch your brother or sister or dog or whatever fish, you can do a static discharge onto them. You've encountered that before. By the way, that static discharge, that little sound you hear, that little tiny sound, is literally thunder. It is the exact same phenomenon as thunder, it's just smaller. So when you hear the thunder coming over the plains in Crawford when there's a beautiful thunderstorm, right? It's the same exact thing. It's just that cloud is shuffling across the land, just like your socky feet shuffling across the carpet, and then just like you touching your dog and go, zzz, the lightning is that exact same phenomenon. They are the exact same. And by the way, if someone ever corrects you and says, you say, oh look, I saw thunder, or oh look, oh I heard lightning, and they say, actually you heard thunder or you saw lightning, it's the same phenomenon. It's just that we happen to have a word for both the sound and the visual, where we don't for most things. Right? Like anyway, it doesn't matter. They're the same thing. They're the same thing. It's one phenomenon that has a different name for how it sounds and how it looks. Most phenomenon, when we see a fish and we hear the fish go blub, we don't be like, that's not a fish, that's a blub that I heard. But people just like to be pedantic about thunder and lightning. They are one phenomenon. What's up?
So when you shock each other, is that static?
Yeah, it's this static discharge is lightning. Okay, so what's current electricity? What's current electricity then, and how is that different? Yeah, okay, so we can have it's when the electrons flow. And so here I have an example of current electricity, and we are going to bring this back to magnetism in a second. But I want to show you my example of current electricity. I have a wire. I have a really jacked up wire. I have a little light bulb here, which because of how jacked up the wire is, I might not be able to get it to hook, and this will be embarrassing. Nope, I think I got it. And I have another wire. Oh, I don't want that. I want this wire. I didn't really want to drop that, but whatever. Okay, I got two wires here. I got what we call in electricity a load. I'm going to put a load is anything that uses the electrical current in a circuit. Have you heard the word circuit before?
Yes.
Circuit is like the path that the electrons flow. And if I attach that, oh, look at that!
Oh.
Ta-da! Oh. Oh. Ah!
One's right there.
Huh?
They're right
Oh, yeah, you're right. Well, we forgot this time, but that's okay. So the flow of electrons, as they pass through the wire, they then pass through this light bulb, and the electrons in the wire, called the filament of the light bulb, go really, really fast, and they get hot enough that they emit light. That's called an incandescent light bulb. So that's one example of the current electricity. And here, where they come together, is where all this comes together is in the concept of the electromagnet. And an electromagnet relates to the phenomenon that anytime electrons are flowing, they generate, because of the EM wave, they generate a magnetic field. So as this is you can't probably see on the camera, but I'm pointing at an electrical conduit, or it's true when you have a charger. Anytime a wire is carrying electricity, it generates a magnetic field, always. Which is why we kind of need to be careful around things like this, because these generate a magnetic field which could also ruin or harm the electronic devices. But any flow of electrons generates a magnetic field just like it generates an electrical current. Those things go hand in hand. Electromagnetism go together. And the example of that, where this comes to our, most of the time where it comes to our real life, is we have these two things called a motor and a generator. And a motor, well, why don't you tell me, what does a generator do? Takes some kind of energy and makes some other kind. Not at its most basic level. It's what kind of energy to what kind of energy? No. Does it take heat? No. What has to be happening with a generator? It must, okay, it must move. So it's what kind of energy? Kinetic. And then because of magnets, you move the magnets and they generate a flow of electrons, which we call what kind of energy? Electrical energy. So if that's what a motor does, or sorry, that's not what a generator does, is it takes kinetic energy. I'm going to show you. It takes kinetic energy, so I'm going to crank the crank, and I'm going to put my light bulb on it. Come here, light bulb. If only I had one more hand. I'm going to put the light bulb, which again, what do we call the object in a circuit that uses the electrons? I just told you. A load. Now I'm going to generate, because there's a magnet in here, and as I spin the magnet, look at that, do you see? You see it? So as I spin the magnet, it generates a flow of electrons, and those electrons again flow through there, and that's what a generator does. It takes kinetic energy from me, in this case, and it makes electric energy. So what might a motor do? Take electric energy and make it kinetic. So instead of this load, I am now going to attach a battery to my, what was a generator. Hold on to this, Gavin. No, you can't, because you can't be on the screen. I wish I had one more hand and it wasn't Gavin's hand. Oh, criminy. Yeah, okay, thank you. Thank you, Justine. Okay. Just put this, I guess, in my pocket for now. And then just while I attach this, and then I'm going to put this in my other pocket. Okay, here we go. Now, check it out. So I'm going to put a battery on this instead. What the riz, she says. That is the most ridiculous thing I've ever heard. But look, now that it has electrical power provided to it, it makes that into kinetic energy. That's what a motor does. They are the same device, right? I just showed you. I used one device. They just do, depending on if you provide electrical energy or if you provide kinetic energy, it does the other one, a motor and a generator. And that's electromagnetism. Because what's the thing in here? What's inside this gray thing making it do that? A magnet. A magnet. So when electrons flow, a magnetic field will move. And when a magnetic field moves, electrons will flow. That's just how it is. That's electromagnetism. Do you guys have questions? Okay, I thought you wouldn't. Bye!